Membrane distillation is a separation technique that can be used commercially for processes such as water purification. The major challenge of using ceramic membranes for membrane distillation is the hydrophilic nature of the membranes. The initial part of this study involves modification of hydrophilic alumina and silica membranes with perfluorocarbons that can alter the hydrophilicity of the surface and potentially work to exclude water from the modified surfaces. The best method of modification was explored through the hydrophobic properties as well as the thermal stability of three different perfluorohydrocarbons, PFOS, PFTSI, and PFBS. Hydrophobicity was measured using contact angle and sliding angle measurements. Contact angle is the angle made between a water droplet and the modified surface. Contact angles less than 90 degrees indicate hydrophilic surfaces. Contact angles between 90 and 150 degrees indicate hydrophobic surfaces, and contact angles between 100 or above 150 degrees indicate superhydrophobic surfaces. Similarly, sliding angle is the angle above the horizon at which water slides off of the modified surface. The lower the sliding angle, the higher the hydrophobicity of the modified surface. To summarize, superhydrophobic ceramic membranes characteristically have large contact angles, are resistant to abrasion, are thermally stable, and have enhanced membrane performance and durability.
Alumina silica ceramic membrane were modified using incipient wetness impregnation method, and acetone was used as a solvent for the modification of this membrane. The hydrophobicity of the modified membrane was measured using contact and sliding angle measurement. Figure 6 and 7 are the contact and sliding angle plot of the modified hydrophobic membrane. Perfluorobutane sulfonic acid modified membrane show least hydrophobicity with contact angle less than 150 and sliding angle greater than 10, while the other two perfluorocarbon modified membranes show superhydrophobicity with contact angle greater than 150 and sliding angle less than 10. 10% weight loading is the minimum percent weight loading that can induce superhydrophobic behavior on the modified membrane, as can be seen on this plot. Below 10% weight loading, the contact angle decreases, meaning the hydrophobicity decreases. While above 10% weight loading, there's no significant change in the contact angle and hydrophobicity of the membranes. This is an image of hydrophobic modified membrane crushed into powder. As you can see, the water beads on the surface, and this indicates the superhydrophobic nature of this membrane. And also, this shows that the modification is not just on the surface, but also within the pores. Here is a traditional hydrophilic membrane, which is completely wetted by water, is crushed into powder. The thermal stability of the membrane was studied using thermogravimetric analysis. So figure 10 here is a TGA plot of perfluorooctane sulfonic acid modified aluminum membrane. As you can see, it maintains its thermal stability up to 300, and after that, it loses its thermal stability and hydrophobicity drastically. So about 10% weight loss here indicate the temperature at which the perfluorocarbon is burnt off the modified membrane. Here is a TJ plot of perfluorotetrahydroazoxylene modified silica membrane. As you can see here, it maintains its thermal stability up to 400, and after that, it's start losing weight. So the weight percent loss here is indicated temperature at which the perfluorocarbon will completely burn. So in discussion, perfluorobutane sulfonic acid modified membrane is the least hydrophobic as it has contact angle less than 150 and sliding angle greater than 10, while the other two perfluorocarbon modified membranes show superhydrophobic behavior. Perfluorobutane sulfonic acid is more suitable for aluminum membrane, while perfluorotetrahydroazoxylene is more suitable for silica membrane, and it shows high thermal stability up to 400 degrees. And this high thermal stability can be attributed to the silane functional group of the perfluorotetrahydroazoxylene, forming a stronger bond with the silica membrane.
In conclusion, hydrophobicity can be tuned with different perfluorohydrocarbons. The optimal loading weight was found to be 10% by weight, and by powdering the samples, we were able to show that the hydrophobic treatment was not just on the surface, but throughout the pores. Also, we would like to note that the thermal stability can also vary with the type of membrane chosen.